Okay. Okay, so welcome everybody to this week's Lithium seminar. Today's speaker is Alberto Morpurgo from the University of Geneva. And as I'm sure many of you already know, Alberto is a world-leading expert in the study and investigation of new phenomena in 2D materials through various transport techniques in, using nanoelectronic devices. And he received his PhD at the end of the 90s in 1998 from the University of Groningen, where he worked on mesoscopic superconducting proximity effect, a work which awarded him the prize for the best PhD thesis in condensed matter in the Netherlands. And then he spent 2 years on a postdoctoral stint at Stanford University. And after that, he started his own group at Delft University, where he initially focused on the study of organic semiconductors and carbon nanotubes, and later started a very successful and long-standing research program on graphene electronics. And since 2008, he has established himself and his group at the University of Geneva, where he's continuing his work on nanoelectronic devices and quantum transport of several families of 2D materials. And at the same time, he's pushing the frontier on the study of doping effects using new ionic liquid gating techniques. And it is a true pleasure to host Alberto today and sort of hear the latest news on the exciting topic of ionic gating studies of 2D semiconductors. So please join me in welcoming our speaker and enjoy his talk.
Thank you, Ricardo, for the introduction, and thank you for the invitation. It's a pleasure to be able to tell you about what we've been doing over the last several years on ionic gating of 2D materials. It's just a pity that I'm not able to be in Boston to also have a chance to, visit your labs, but that's the way it is. It will change soon, I hope. So what I really would like to try to do today is to show you that ionic liquid gating, at least on a certain class of 2D materials, has moved to a different level where we can control things better. And do pretty quantitative measurements of different types, or do more sophisticated experiment that it was possible in the past by controlling device fabrication technique or device fabrication using structures that are now becoming possible to realize with 2D materials. So the main part of my talk will be about different aspects of semiconductor physics that we can address with ionic gating. But I will also say something about gate-induced superconductivity, which maybe is a more commonly known topic that comes out when you discuss ionic gating. These are the people involved in the work in my group that have been involved over the years, so some of them are still around. We have benefited a lot from materials grown in Geneva by Enrico Giannini, Salim Barreto, and also Helmut Berger, who is a crystal grower at EPFL, or I should say was, because he has retired a few years ago. It's a pity because he was growing some of the most purest transition metal decalcogenate crystals that I have seen. So this is an outline of what I would like to tell you about. I will start with a very short introduction about gating, because I'm sure you know everything there, and I introduce ionic gating. It's a pity, it's maybe difficult to ask questions, put them in the chat, because I don't want to, I see from the other talk in this series that I guess most of the audience is really made of experts in the field, so I don't want to, to bore you with things you already know. Then I will spend some time telling you things that is not what I want to tell you about, which is indeed gate-induced superconductivity, to focus on some aspects of it that are maybe less commonly discussed in other talks. And I will then move to the main part of the talk, which is what I really want to tell you about, which is semiconductor physics. And in particular, there will be two topics. The first one is that you can use ionic gate to do quantitative spectroscopy of energy level in semiconductor, in particular to measure band gaps, band alignments, in a very precise, as I try to convince you, way on 2D semiconductors. And the second part, I will show you that by developing new type of devices, in fact, double ionic gated devices, we can apply electric fields that are impossible to reach with conventional dielectrics, so large that we can basically close the band gap of 2D semiconductor band gaps of the order of, say, 1.5 eV or even a bit larger. So that's the program for today. Let me start with it. So for the motivation, I mean, I guess you guys all know what is a field effect transistors, and you have a gate, which is a metallic electrodes, And you use that to apply a potential to attract charge carriers at the interface, at the surface of the semiconductor, where the semiconductor is separated by the gate by an insulator, so that you can control transport from a source and drain contact. And a basic equation that will come over and over is this one. When you apply a gate voltage, essentially you're doing two things. You're applying an electric field, or there will be part of the gate voltage will go in electrostatic potential difference between the gate and the semiconductor, and part of it will shift the Fermi level. So essentially, your gate voltage is a change in electrochemical potential. And what you like to do, if you're interested in, for instance, in accumulating as much charge as possible, what you really would like to do is to have the biggest possible shift in Fermi energy in your system. However, because you have this contribution coming from electrostatics, necessarily some part of your voltage will be sort of wasted in creating an electric field. And now, if you are able to boost the capacitance of your gate relative to the semiconductor, you are able to waste less and less of this gate voltage, and put more and more of your applied gate voltage into a shift of Fermi energy. And so that's the entire point, in a sense, of the ionic gating, to try to do something which has a very, very large capacitance, so that you're able to neglect this term. And I will see how this plays a role in several different circumstances. So that's the goal of ionic liquid. In an ionic liquid, what you don't have that a real, say, a solid state dielectric is separating the gate from the semiconductor. In this case, the gate is a metal, can be a physical wires in ionic liquid, could be a metallic pad on the substrate. Doesn't really matter where it is, because what happens is that you apply a voltage between your gate and the device, so the contact in the channel, so to speak. You apply a gate voltage between the gate and one of the source and drain. But the ionic liquid is formed by molecules which are charged, and the density of charge in the liquid is basically like in a metal, which means the electrostatic screening length is as short as in a metal. So what happens in a metal is, if you apply a voltage, the electric field is screened at the surface, the metal is equipotential, and you have voltage drop only at the two interfaces between the metal, in this case, between the gate and the liquid, and between the liquid and your surface here. And the thickness of this interface is of the order of the screening length, which in these systems is less than 1 nanometer. And so you can try to estimate what is the capacitance of these interfaces, and it is actually huge. Is 50 microfarad per square centimeter, which is basically 1,000 times bigger than the capacitance of 300 nanometer silicon oxide that you normally use, or that is commonly used in many of the devices we do with 2D materials on solid state substrates. Because of this very large capacitance, we can, by applying a very small voltage, we can accumulate density which are really unreachable with conventional gates. So we're talking about a density which are larger than 10 to the 14 per square centimeter. We can, and so one thing that we learned over the last several years is that this technique is very powerful, but it doesn't work with all materials because of a number of reasons. So for one of the reasons is that the electric field at this interface is really strong, and some materials are not able to withstand it. So for instance, transition metal oxide, in many, many cases, I would say in majority of cases, have the oxygen atom pulled out because there is a charge on the oxygen, and the electric field just pull out the oxygen atom, and so you're actually degrading the material. So every time you use this ionic gating technique, you should be careful that you have reversible behavior, that you can reproduce everything you measure, and that you don't have irreversible degradation or changes in the material. Sometimes it's not even degradation. Sometimes you can use the technique to control how much oxygen you remove and to create control of the oxygen vacancies. In our case here today, we'll only discuss about electrostatic effect, where the materials is not changed by the application of the liquid. One parameter which is technically important, I mention here because it will come to be important when you actually do things, is to have what is called a reference electrode. And the terminology comes from electrochemistry, and is something I'd like to know more about, and I know very little about, but the idea is simple. It's basically, if you apply a gate voltage and everything works as it should, essentially you can view your device as two capacitors in series. One capacitor is the capacitance between the gate and the liquid, and the other one is between the liquid and your in your device. And when you have two capacitors in series, the voltage drops across the smallest of the two. That's one reason why you make your gate normally very, very large, so that you can neglect the voltage drop at this interface. But no matter what, if you put a reference electrode, it's basically a metal which is in contact with the body of the liquid, and so it measures the potential of the liquid. And no matter what happens, if you essentially the reference potential give you the difference of potential between the body of the liquid and your semiconductor, so the actual gate voltage you're applying across your interface. And so it's important to see that everything works properly, to measure, for example, the reference potential as a function of gate. And if everything works properly, you find that there is basically a linear relation with slope 1, although there can be an offset because of built-in potential. But there is, when things are working properly, there is sort of efficiency close to 1 if you have made your device correctly and if there is no problem. So this is basically the basic concept of a ionic liquid gate. It's a way to apply very large charge density, to accumulate very large charge density, and it's sort of you can think of it as a gate with a very, very large capacitance. Okay, so that's the short introduction. Here is what I will not talk about, which is gate-induced superconductivity. Sorry for the slide that is, I see this figure is cutting part of the text. So because it's possible to accumulate so much charge density on these systems, this ionic gating was initially developed. In fact, it was initially developed about 20 years ago in the context of organic semiconductor, which is what I was working on 20 years ago. And there it was used for a different purpose. It was used because because of the larger capacitor, you could use organic transistor at small voltage, which is an issue. But some of the same people, in particular Yoshi Wasa, University of Tokyo, who was working on organics, started to apply ionic gating to inorganic materials. And one of the first materials that he applied to was molybdenum disulfide. And he was able to discover that when you go to sufficiently high gate voltage, you can accumulate so much charge that this material, which in its pristine form is an insulator, the surface of the materials become a metal and eventually become a superconductor with actually a pretty nice critical temperature. The highest critical temperature at about 10 to the 14 per square centimeter electrons accumulated on the surface is 11 Kelvin, which is seriously high. And so that attracted attention of the community. It certainly attracted my attention. At that time was one of the first observation of gate-induced superconductivity. By now there are many more examples. And so there have been a lot of work. And one of the problems with this, so where we entered the game was actually quite a bit later. We were able to show that not only thick layers, which is what Yoshi had focused on, become superconducting when you use a gate voltage, but we could gate-induce superconductivity down to the monolayer of molybdenum disulfide. There is still stuff that needs to be understood. For instance, it's quite unclear why the TC of these systems depend on thickness. It's quite unclear because the materials itself is an insulator. So, it doesn't really matter. It should not really matter, one would think, if you make the materials 5 or 6 layer or 2 layers, because in fact, at the density that you accumulate, essentially all the density is in the top layers. And instead, there is a systematic behavior, we find, of TC that become smaller as you reduce the number of layers. So that was interesting, but it's, again, not what I want to talk about, even about superconductivity. The point is that essentially all these studies, because were made by studying superconductivity by transport. And transport, is very nice to see that you have superconductivity because you see a zero resistance state, but it gives almost no information about the nature of the superconducting state. And so that is a bit frustrating because you really like to see, to understand more what is the nature of superconductivity that you induce on this material. And in fact, there start to be more and more theoretical work about this, and it's nice to be able to say something experimentally. And so one thing that we did, and that's what I would not like to tell you about, is tunneling spectroscopy on this gate-induced superconducting system. And basically, one would think that it's complicated to do tunneling spectroscopy because you have the liquid on top of your materials, and then if you think about STM, you would not be able to to bring the tip in proximity of your gate-induced superconducting layer because there is the liquid in between. And so what with the development of fabrication technique based on van der Waals layers, we were able to have this idea, to implement this idea, to use multilayer graphene as tunneling contact and to use say fairly thick, where fairly thick means 7-8 layer molybdenum disulfide, so that when we accumulate with charge with the liquid, we accumulate the electrons on the top layer. And again, the screening length for the density of superconductivity is 1 or 2 layers. And so you find yourself in the situation where your tunneling probe, which is this multi-layer graphene, is separated from the accumulation layer by several layers of molybdenum disulfide, which are not where there is no charge accumulated. So you have a band structure of this type. You're accumulating charge at the surface. You have the Fermi level in the graphene here, and for most thickness, for the largest part of the thickness of molybdenum disulfide, the Fermi level is in the gap. So you have actually a pretty thin barrier, but it's still a tunnel barrier. And at low temperature, when you can reduce thermal activation, you can tunnel treat, and you can try to do tunneling spectroscopy of the gate-induced superconducting layer in this system. And so that's one of the things we did. We did it at different gate voltages. We could correlate. We actually could probe tunneling spectroscopy and transport in the very first layer, because I mean it's one layer where there is charge accumulated. It's in that layer there is transport, and when you tunnel in that very same layer. We could do that as a function of density, and what we could find is that there is indeed a gap that opens in correspondence of the transition. So you can measure the resistance transitions. Sometimes the resistance transition is sort of lousy. This comes from some cracks that you have in the liquid at low temperature, which generate some region of the materials which have higher resistance. But so as you see here in this case, where the resistance transition is lousy, the suppression in density in tunneling conductance is even better than in this case where the transition is nice. So there is no really correlation between. We find that there is no correlation between these the quality of the resistance transition and the quality of the density of states. And the most striking thing we find in all devices we measure is that it looked like there is not a complete gap. There is a suppression of the density of states, but you know if you talk about BCS lobes, if you can they are at a voltage that depends on the density you accumulate. So here we are at optimal doping, which is about 10 to the 14. Here we are sort of overdope, where TC is quite a bit lower, so the gap is smaller. But we see that we have the resolution to go significantly below the gap, and we see that we don't have. If it would be a fully gap system, we should have a completely flat tunneling curve here at the bottom with the conductance, which is tunneling conductance, which is basically zero. That's not what we see. And to try to analyze these a bit more in detail, we can take advantage of the fact that we can change the density with the gate and use the fact that unless there is a phase transition in the nature of the superconducting state as a function of density, in the theory of superconductivity, the Fermi energy doesn't really enter anywhere. So we can try to analyze our data in terms of reduced variables and plot our data as a function of voltage applied to the barriers divided by the gap that we extract from this curve. And then we see that things tend to collapse. And now this way is difficult to implement precisely because every curve has to be measured at the same reduced temperature. And when you take data at a fixed number of temperature, TC is different. So you never have curves which are exactly at the same value of T over TC. So that is responsible for quite a bit of the spread that you see at low energy. The spread that you see here close to the gap, this is coming from inhomogeneity on the system. But here at low density, which is where we are more interested in to see, if superconductivity is really gapless, this we can do better by looking at not the entire DIDV curve, but by looking at the IDV curve of V equals 0, because no matter which temperature at which temperature we do the measurement, we always have the tunneling conductance of V equals 0. And so we can plot that as a function of T over Tc, and then we take all the devices we measure, and we see that at small T over Tc, essentially the data collapse on a curve which is sort of linear in the tunneling conductance is linear in temperature. It's not exponential as you would have if you would have a full gap, and it's up to 0. And we see that in the device where we are able to go to the lowest T over Tc, we have a suppression in tunneling conductance which is close to 95%. But it's not an exponential, or we still have a finite linear in energy, in temperature, tunneling conductance. If you analyze this, it basically means you have a linear density of state starting from the density of state goes to 0, the Fermi energy, but increase linearly, and there is not a full gap. So this is a direct indication that superconductivity in this system is unconventional. What exactly is the nature of the unconventionality, we do not know yet, and that's why this is not the really what I would like to tell you about, because I think there is much more that can be done in this system to study superconductivity. That's something that we are working on, that we plan to do more in the future. The reason why there is more to be done is because now we are studying gate-induced superconductivity in a class of systems. I mean, superconductivity is seen in all these systems, which we can study a semiconductor, and we can characterize with technique that we know very well to understand a lot of the electronic properties. And ab initio calculations seem to work pretty well for this system. So we have a system which is quite a bit under control. For instance, and I will not, I mean, these I'm just flashing the references. We have been studying Raman as a function of density in gated devices. And we found that by analyzing the data, we found that electron-phonon interaction is very strongly enhanced when you start to fill two valleys. At the beginning, at a low density, you have charge carriers only in one valley of the band structure of the TMDs. But at high density, you start to fill two valleys. And we find that from our data that electron-phonon interaction become much stronger when you fill two valleys. And it really seems from the data that that's when superconductivity happens. Okay, now the fact that superconductivity is mediated by phonon does not mean that it's conventional superconductivity, and we are trying to study that theoretically with a number of people. Other advances that we are having, and I will say something more in a bit, is that by looking at quantum capacitance or capacitance effects, we are able to find the position of the Fermi level in the bands. And that's something that also until now was difficult to do because, you know, if you don't have Schönigel oscillation, if you don't have other quantity that you can measure, it's difficult to identify exactly where the Fermi level is. And now we start to be able to do it. So I think there is a lot of room to go pretty deep to use this as a model system to study unconventional superconductivity and understand quite a bit about it. And that's one of the things we are working on, and we'll do more in the future, I hope. So having said what I did not want to tell you about, I'll move on to the main topic. And this is as I said, there are two subtopics. And the first one is what I call ionic gate spectroscopy. And it is a way to use ionic gating to do quantitative spectroscopy of band edges in 2D materials. And let me show, we go back to to this equation I showed you at the beginning, which again is pretty important. And here you see data measured on molybdenum ditelluride transistors. So these are exfoliated molybdenum ditelluride thick means they are thick enough that you can consider them as bulk. They have a room temperature gap of about 850 millivolts. And now these are devices with different gate capacitances. So the top device is made with the conventional 200 nanometer silicon oxide gate insulator. The capacitance of the gate is 12 nanofarad per square centimeter. And you see that, you see ambipolar transport. What does it mean? It means that with a negative gate voltage, you can put the Fermi level in the valence band. With a positive gate voltage, you can put it in the conduction band. But the amount of gate voltage you have to apply to go from the valence to the conduction band is pretty big. It's way bigger than anything related to the gap, which is less than a volt. And what does it mean? Well, it means that the capacitor is small enough that in this case, this guy here, this term on the right, is the one that dominates. So you have to spend most of your gate voltage to create electric field and not to shift chemical potential. And that's why, the gate voltage is so large compared to the gap. Now we can just go sort of increase the capacitance by an order of magnitude about. So you go to 170 nanofarad per square centimeter, 15 times larger. And the curve is qualitatively similar. You see hole conduction, electron conduction for opposite. I guess there is something wrong with the scale here, I guess. I guess these, no, okay, so the reference potential, again, this is what comes if you have a reference potential, never mind this. So what you see is that the interval where you have no current is 2.8 volts, which is bigger than the gap, which is 0.85 volts, but it's started to be comparable, which means that this term is still dominating, but it's not so much bigger than this one. So when you change the gates, you're changing both. This dominates, but this you cannot neglect. And now let's increase the capacitance drastically. We go to ionic liquid. The capacitance is about 50 microfarad per square centimeter. So we are going up almost to the magnitude. And now let's look at the curve. The difference between the threshold voltage for holes and threshold voltage for electron is 0.85 volts, which is pretty much the gap of this material. What does it mean? It means that we have increased the capacitance so much that this term now you can basically neglect it. And you are just shifting with your gate voltage, you're shifting the chemical potential. So when the chemical potential is at the threshold voltage for holes, that means that you're putting your Fermi level just at the edge of the top edge of the valence band. You now apply a gate voltage, you shift the chemical potential all the way to the bottom of the conduction band, and that's when the electron threshold is. That's where the electron threshold is. And so the difference in this chemical potential is pretty much the gap, and so that's what you're measuring. The difference in threshold voltage is equal to correspond to the difference in chemical potential when you're at the conduction band minimum or the valence band maximum, and that's by definition the gap. And indeed, the gap of these materials is 0.85 volts. So that is a benefit of having such a very large capacitance, which goes beyond just being able to accumulate a large amount of charge carriers. It starts to give you quantitative, the ability to measure quantitatively certain quantities, which are not easy, because if you go to 2D materials, we know that, it's not straightforward to measure the gap. If you measure photoluminescence, for instance, you have very large axion binding energy, and what you measure is not the gap. Instead, this is the band gap. So the first time we saw this was already close to 10 years ago, and we saw it, we're starting to do our first ionic gated devices on again, what we would call bulk tungsten disulfide, like exfoliated flakes of the order of thickness 10 nanometer. We saw beautiful bipolar curves. And what we were struck by the fact is that the difference in threshold voltage for holes and for electrons was precisely the gap, 1.4 volts, which is the gap of bulk tungsten disulfide. At that time, we thought, okay, look, great. We found what we think is the right explanation, the explanation I just gave you. But we thought, okay, this works because this tungsten disulfide is an extremely clean material. These were crystal grown by this guy, Helmut Berger. They were probably he was doing vapor phase transport for 3 months to purify that as much as possible. And we thought, it just worked because this stuff is so clean, and this guy Berger is amazing, which he was. And in fact, we did the same experiment on monolayer, on bilayer. We got the value of the gap that are expected to be right. So here you see the extrapolation to get the thresholds. We found that the gap decrease in thickness. In fact, you can, on these same materials, you can measure photoluminescence, and then you can look the energy at which photoluminescence has. You take the difference between the two, and this gives you the axion binding energy. So you can measure the axion binding energy because you can measure the gap and the recombination of the exciton independently. Clearly, this is the axion binding energy of a system which is in contact with ionic liquid, which has certain dielectric properties. Still, we get 200 millivolt axion binding energy, which is pretty large, and it is of the order of magnitude that is expected for this 2D system, because in 2 dimension, the effect of electron-hole interaction is pretty strong. And so we find that axion binding energy for the bilayer is smaller than the monolayer, which is what you expect. So this all is going into the direction of showing that this stuff is working quantitatively and give quantitative measures. And so the measurement we did on tungsten disulfide is summarized here, where you see the bulk, bilayer, monolayer, all giving the right values. But it was only when we got to measure these materials, molybdenum ditelluride I already showed you, and rhenium disulfide, and these crystals were certainly not very clean. We had a lot of indication in molybdenum ditelluride. There were plenty of defects inside the gap. And still, when we do the experiment, we get the right gap value. And it's again because this capacitance is so large, and even with a fair amount of defects in the gap, the charge you accumulate is the electric field associated with the charge you accumulate can be neglected compared to the changing in chemical potential. So the technique is actually quite reproducible. So this is measurements that we have done on monolayer tungsten disulfide. So these were about 10 devices. We might have more. These were experiments measurement done in different projects by 3 group members, so different person, with 2 different ionic liquids. And you find that the spread in values, despite the fact that it's different person with different liquids, is actually pretty small. So the technique is actually precise, and it's simple and precise. And having a simple and precise technique to measure gap values in 2D materials is something which is useful. So we have done this measurement quite systematically, not necessarily because we want to compile this data set, but because in different materials we were in different experiments we were using different materials, and we ended up measuring their gap. The molybdenum disulfide give a incorrectly large gap, and we know the reason. And the reason is because there are states. There is close to the valence band. There is in monolayer molybdenum disulfide, there is a density state coming from sulfur vacancies. And so when we shift the chemical potential to put it in the valence band, we need to fill the states. And then this condition that that we can neglect, you know, the electric field associated to the charge is not valid anymore, and that results in these anomalies. Large value is a few hundred millivolts bigger than what it should be, but all the rest is pretty much consistent with what is known to be the gap of these materials. Maybe one thing which is still worth emphasizing is that the technique does not only work to measure gaps of one material, but you can also measure band alignments of different materials if you do devices with the right structure. And again, measuring band alignment is not something super simple in general. It might depend on a lot of things. But the idea is the following. You can, you know, take two different materials. In this case, these are tungsten diselenide and molybdenum diselenide. You can make an iterative interface in such a way that you can put contacts on, you know, all the different parts, material A, so molybdenum diselenide, tungsten diselenide, and the interface. And then you can do your ambipolar transistor curves by measuring separately each one of the materials, and you find nice ambipolar transport on each one of the materials. And then you plot them on the same plot, and you find that when you measure the interface, which is the red curve here, as you accumulate electrons accumulate electron interface, you get a conductance, which is, or a conductivity, which is, in this case, I plot the current, but it's identically coincide with the conductivity that you measure when you measure the molybdenum diselenide. And instead, when you accumulate holes at the interface, your conductivity coincides with the conductivity that you measure when you measure tungsten diselenide. So you see that, you know, the interfacial curve. And so what is this telling you? Is a direct demonstration of the fact that at your interface, the conduction band is inherited from the molybdenum diselenide, and the valence band is inherited from the tungsten diselenide. And you can just measure the different threshold voltages, and you know what are the distances in band edges of these different systems, and you can make a band diagram. And so, and again, this is pretty precise. So this is a simple way to get the energetics and the band diagrams of even pretty complicated structures, as long as you're able to see ambipolar transport with ionic liquid gate, which is not true for all the system, because as I said at the beginning, in some case, the material may be unstable, but if you can do it, the technique basically works. One thing that we are looking at, and this is something that is giving interesting surprises, but is in terms of spectroscopic capabilities, is still not giving what we would like to give, but is try to see whether we are able to understand things, not only when we sweep the chemical potential through the gap, but also when we start to put the chemical potential inside the bands. Okay, one thing, so these data are taken on monolayer molybdenum diselenide. We would have similar data on other monolayers. And the interesting things, again, if you look at your gap in your ambipolar curve, is what you expect it to be. And then here we measure these dots here or here, the density measured by Hall effect that we accumulate as we enter with the chemical potential in the conduction band or in the valence band. And the thing which is really interesting is the fact that, you know, the slope of this curve changed by quite a bit, is close to a factor, is more than a factor of 2. As you pass a certain value. And what does it mean? It means that your capacitance is changing by more than a factor of 2. And why is that? Well, okay, the obvious explanation is that the total capacitance that you're measuring in this device is the geometrical capacitance plus the quantum capacitance added in series. And so the fact that now the geometrical capacitance is huge, so this term is really negligible. So most of your capacitance is dominated by quantum capacitance. So you see huge effect in the quantum capacitance of these systems, because you see, I mean, you see that essentially, and so you start to be able to measure density of states or ratio of density of states. In fact, what we found is that if you now analyze the data quantitatively with the common wisdom or common knowledge of quantum capacitance, we find that things don't actually match quantitatively. I mean, qualitatively all is good. And there seemed to be an additional contribution to the quantum capacitance as compared to what we normally think, which is sort of the compressibility of the electrons is what you normally associate the quantum capacitance with. But there seemed to be an additional contribution, and we have a theory paper also to show that in fact this contribution must be there, and then we claim that that's what we see in our experiments. And this contribution is coming from correlation between electrons that you accumulate and the counter charge in the gate, which would be in our case the ionic liquid. And so this gives an additional contribution to the quantum capacitance, and that's something that certainly is worth studying in much more detail, because this is limiting the total charge that we can accumulate. If we would understand this, we might be able to create condition to accumulate even more charge. And you could imagine that, for instance, a context where this is particularly important is batteries. If now we have a similar effect of quantum capacity at the interface with a battery, and we could increase the accumulated charge density by a factor of 2 or 3, I mean, for batteries, that would be a big thing. So that's something which we sort of came across recently, and it was pretty unexpected. So with this, I would like to go to the last part, the second part of the semiconductor physics that we are doing with ionic gating. And it's about quenching the gap of 2D semiconductor by applying a very large electric field. It's something that it's under review. You can find a preprint on ConMat. So the idea is the following. If you take a gap, and this is a sort of a quantitative picture, of course, the full quantitative story is a bit more complex, but to give you an idea of what we have in mind, the story is as follows. Imagine to have a 2D material, which is a fairly thin, is like a few layers, and then you have a band gap, you have the valence band, the conduction band. Now, if you apply a very large electric field, you can bring, for instance, the top of the valence band on one surface, above the bottom of the conduction band on the other surface. And if you do that, you have basically closed the gap. There is at all energy in your systems, at all energies, there are states. And now if this is a 2D material which is thin enough, the wave function on the two surfaces will extend for a few layers or 1 or 2 layers even, and they will overlap. And so what you actually have done is really you have modified the band structures. I mean, this is a sort of a semi-classical picture, which certainly does not hold quantitatively when we get to this atomic scale, but to give you the idea, that's why I'm showing it. And as the wave function would overlap, then essentially you have states at all energies and you've closed the gap, you've modified the band structure. So that's what you see here from ab initio calculations. This is the band structure of pristine tungsten diselenide. I think is a 4-layer. As you increase the electric field, you find that the gap closes, the bands deforms, and you can do calculation for different thicknesses. You find that electric field closes at smaller field for thicker layers, simply because what counts is the potential difference. So if the gap is about the same, there are different effects here playing a role. The fact that what counts is the potential difference, but also as you change the thickness of the layer, the gap changes. So this effect had been predicted for the first time, as far as I know, about 10 years ago. And this effect in TMDs had been predicted about 10 years ago by these guys here. Of course, we knew even before that we can change the band structure of 2D materials by applying a perpendicular electric field, because in bilayer graphene, it has established that we can open a gap by putting a perpendicular electric field. But bilayer graphene is an ideal condition to be able to do that, because you start from a zero gap semiconductor, and if you go to low temperature and open even a pretty small gap, you will see a very large effect, because you turn a metal into an insulator. Now, if you want to do it on TMDs, it's a bit more tricky, because you start from gaps which are about 1.5 eVs, and either you're able to change them by a large fraction of the gap itself, which requires a very large electric field, or you will not see a really a major effect. So we set to try to see whether we can do this. And the idea was, with ionic liquid, we can accumulate a huge charge density. Can we also find a way to apply a huge electric field? And I personally had this in mind for quite a while. And what I really was not able to do is to think, how can we do a double gated device with ionic gating? Because, ionic gating, we normally use ionic liquid, and you cannot put 2 decoupled liquid on top and on the bottom of a device, at least not easily, because at least that's what I was thinking, you cannot do fabrication on top of a liquid. And so the answer to that came at some point. In fact, I was at a conference with Yambo Zhang, and he was doing chemical intercalation of lithium by using what is called a lithium ion glass substrate. So it's basically a ceramic filled with lithium. What the Yambo was doing was using this system by applying a very large voltage to push lithium out and put it and intercalate it into a 2D material which was at the surface. That made me think that we could use the same system to not do intercalation, but just to use it as an electrolyte, and so to use for gating. And so that is what we set out to do, and we could show. And we went on negative gate voltage intentionally to pull away the lithium from the surface, so that we are sure we're not intercalating. And we could see nice transistor action. We could do what is called ambipolar, light emitting transistors. What you see here is that you can bias your transistor in such a way that you inject electrons and holes at opposite contacts. And then you see that you have a sort of a light coming out and then being emitted from the transistor channel. And as you change the bias, it's shifting the transistor channel. So basically, the experiment showed that you can use this lithium-ion glass substrate as electrolyte for gating. And the reason why it was interesting for us was because now we did have the second electrolyte on which we could do fabrication and do double ionic gating. And so the device we really had in mind to do from the beginning was something like this, where we have our solid electrolyte on the back, and then a multi-layer TMDs, which could be as thin as a bilayer. As we'll see, I mean, we get data on tri-layers, and so you can make your transistors by putting contacts, and on top you put your ionic liquid. And of course, you want to decouple the two electrolyte completely, one from the other, because you want the potential on the ionic liquid to be determined by the top ionic gate and the potential of the lithium-ion glass to be determined by the back gate. If you would have the two electrolytes in contact, they would go to some equilibrium potential and you could not control them independently. So that's why we put sort of a ground plane everywhere except on the TMD. So you're able to establish a potential difference across the TMD only, and the rest is screened by this metal plate. And in fact, you know, we can put reference electrodes to check that when you apply a gate voltage on this side, we are not affecting the potential of the liquid. We can check those things experimentally. And the idea is to apply a large negative gate voltage so that we don't intercalate lithium in any case, and a large positive ionic liquid voltage. So we are going to establish, we basically put, say, holes with the back gate, and then we remove them with the ionic liquid gate. And the only thing which is left, there are no charge carriers because we remove them, but what is left is a perpendicular electric field. And so that's what the experiment is about. And now, if you start to do the measurements, what you find is that when you measure with the back gate at zero ionic liquid, so you sort of don't use the ionic liquid gate, you see the usual transistor curves. Same story. If you put the back gate to zero and you measure with the ionic liquid, you just see, you know, transistor curve, threshold, electron conduction, hole conduction, nothing strange. What is becoming interesting is when you start to play with both gates at the same time, because then you see that if you go negative with the back gate, but you start to put the top gate more and more positive, you start to have a minimum conductance, but the conductance does not go to zero. You're not switching off the channel anymore. In fact, the highest conductance you can get. So here we have, I think, 50 millivolt applied. We have 10 microampere. So we are talking about 5 10 kilo minimum. The minimum is 510 coulombs. So it's something which is sort of well below h over v squared. So this is by all means what one would consider a metal. So it's maybe better to plot this data in a color plot. Now this is a log scale, and again we can go negative with the back gate at zero ionic liquid gate, which is this curve. So we are moving here. We can do the opposite. And now we can play with both gates. And so imagine we start from this point. So this point is here. So we have holes. There is no doubt we have holes. We just apply a negative gate on one of the negative voltage on one of the gates. And then we start to increase the ionic liquid with positive. So the total gate voltage here, well, I mean, the positive gate voltage on the ionic liquid compensate the negative gate voltage on the back gate. And you would go to zero electrostatic potential, essentially. You would expect that you should go back with your chemical potential inside the channel and so have no conductance, but no, this stuff is still pretty highly conducting. And then we can still shift the back gate down to zero and we go to C where we are here now. And so we go from hole conduction to electron conduction without ever shutting conduction off. And so really the only way in which this is possible if at some point in this path, the conduction and the valence band overlap, because if we put the Fermi level in a gap, we should have a very highly resistive state, and we don't have it. So the resistance here is always kind of 10 kilo at most. So maybe a better way to look at this data is by changing variables and plot the measurement as a function of the sum of the potential. So the capacity of the two gates to the TMD is basically the same. And so we can plot the data as a function of the sum of the potential, which determines the potential of the channel, and of the difference of the potential, which is sort of proportional to the electric field. And I will get quantitative in a moment. And now this is what you see. And if you take cuts, you see that, you know, at small electric field, a small difference of gate voltages, you still have a region where the conductance is fully suppressed. At some point, the suppression is basically start to vanish, or you can measure this by looking at the threshold voltages that I showed you before, that they are a measure of the existence of a gap, or in single gated device, they really give you the gap. And so you end up seeing that at some point the threshold voltage for electron and holes, they touch. So there is essentially no, I mean, that's when the gap closes. And so you can do this, and you can do this analysis, and then plot the difference in threshold voltage, and you find when this disappears essentially. We can estimate the electric field because in a first approximation is just the voltage drop divided by the thickness of the TMD. And the reason why this approximation is actually pretty good is again because the capacitance of these gates is very, very large. So you can do a better estimate by looking at displacement field and considering you can write this estimate correctly in terms of capacitances, and you find that basically because the capacitance of the TMD, so epsilon 0 divided by the thickness of the TMD, is quite a bit smaller than the gate capacitance. This term is negligible, and well, I mean, it's a more correction, and our electric field is basically the voltage difference divided by the thickness of the electric field. What that means in our measurement is that we arrive to electric field which are bigger than 2 volt nanometer, which are well above the breakdown field of essentially all dielectrics. The reason why that is possible is because dielectric breakdown is not really the electric field at which you destroy the material because the electric field is too loud for the material to survive. The electric breakdown mostly come from a sort of a leakage current which dissipates some power in the dielectric, which enhances the temperature and increase the leakage current and give you an avalanche process that eventually breaks down the dielectric. So the biggest field we could apply, I think, is close to 2.5 volts per nanometer. We were able to close the gap in down to tri-layer. We could not close the gap in bilayer. I mean, that is really close to the maximum electric field that eventually, break down things. And we have seen this in different thicknesses and in a number of different devices. We can then plot that this electric field that is needed to close the gap as a function of thickness. So this is the crosses. So the full dots here are the result of ab initio calculation, which are a bit smaller electric field unit, but it's known that ab initio calculation underestimate the band gap. And if you change all this value by the ratio of the known gap to the ab initio gap, you get the empty circle, which are basically in very good agreement with what we measure. So essentially, these results show that we can, quench the gap with this electric field, and then the question is, what is the nature of the electronic state that we create when we change the gap, and that of course require more investigations. But the electric field that we have been able to apply to reach this is larger than 2 volt nanometers because we go well above to the field that you need to close the gap. And so this is basically what I wanted to tell you about today. So mainly about advances in control of ionic gating that we have been able to achieve working with 2D materials and especially TMDs, where everything works really nicely. I discuss in detail how you can use this to do quantitative spectroscopy of band gaps. I show you how you can use this to tune the band gap and even close it starting from a material which has a 1.5 EV gap. And what I did not tell you about is tunneling spectroscopy of superconductivity, which is work in progress. So thank you for your attention. I'll be happy to have any question you might have.
Okay, thanks, Alberto. I'm gonna applaud on behalf of everyone, although this doesn't quite make the same job as a full room people. But yeah, thanks for the very interesting talk. I see there are a couple of questions in the Q&A tab. I also have a question myself, but I'll go first with the questions that have been asked in the Q&A. So the first question is, someone is wondering if adding ionic liquid to a field effect transistor would affect the switching speed negatively because of the fact that one would like to reduce the additional capacitance in the MOSFET to increase the switching speed. So what would you expect the
I think it would affect the speed much worse than what you have in mind, if that's the effect you have in mind, because ions are slow. And so if you want to have a very fast device, that you should not use device based on ions. These devices are devices that you want to use. You could imagine to use them on, for instance, imagine ideas you have in mind is that if you like to have a tunable light source, then you don't particularly care whether you switch it, fast or not fast. You care that you can, for instance, change the emission spectrum by a lot. And okay, so that would be possible. I mean, that's the kind of thing we're looking at. If you care about fast electronics, forget about ions. You should not look into ions.
Okay, thanks. So the second question by Tai-Hee Kim, I'm hoping I'm pronouncing the name correctly, is about whether you've done any temperature studies on the band gap quenching. Is this something you observed only at room temperature? Did you look at the function of temperature? Did you see anything there?
Okay, so no, we have not yet done things as a function of temperature, but it's certainly something on our agenda. The reason is if you want to do things continuously as a function of electric field, you need the ion to be mobile, and ions are mobile only at pretty high temperature. If you take an ionic liquid, at low temperature it freezes, so you will not be able to sweep gate voltages. So the way to work at low temperature is to bias your device at high temperature and cool it down, work at that density electric field, and then you need to warm it up and change the bias. So it is pretty painful to work at low temperature, and for the time being, we mainly focus on controlling the band gap, and because the band gap is 1.5 eV, we don't have any problem with the band gap being much bigger than KT. I mean, we are not limited by resolution due to KT, so that stuff we can do at room temperature. We plan to look at optical properties at room temperature, but certainly it will be very interesting to measure what happens at low temperature, because, for instance, there are also predictions that if you close the gap in TMDs, what you might be getting is a topological insulator. And so it will be very nice to see whether we will be able to see it or not. I can imagine that some difficulties will come from the fact that, you would open a new gap, which is much smaller, which is coming from spin-orbit interaction. And then if you have potential fluctuation coming from the fact that you have discrete ions next to the channel, that might be problematic. But I mean, there is interesting physics that requires going to low temperature, and we'll certainly do it. But we have, this stuff is sort of, we managed to finalize this stuff fairly recently, and we've not yet did it. We have not yet done it.
Work for the future, yeah. So the next question is from Philip Kim. So Philip is asking, for multi-layers, there is more carrier accumulation on the surface, and the induced carrier density decreases away from the top surface. How do you take into account such carrier distributions?
I'm not sure in which case you're referring to, but in the case of superconductivity, the density at which you basically have all the carriers in one layer. If you're talking about the part where I'm discussing the gap closing, basically the accumulation of charge at the beginning. So as soon as you put the first charge, the length scale is determined by the screening length, by the electrostatic screening length. And at low density, the electrostatic screening length is pretty long. So if you're looking just, when you close the threshold, you're looking at regimes where the density is very small and the electrostatic screening length is pretty long. So the charge is not really localized on a layer. It's going to be distributed on entire thickness, and so it's well compensated by the two gates at the same time in that first approximation.
Okay, I hope that answers Philip's question. If not, feel free to write a follow-up. I'll move on to the next question. Is from Kenji Yasuda. Kenji is wondering if it's possible to apply an electric field in the opposite direction and still close the gap.
Okay, so that is something we're working on. I think as I said, we would rather avoid going positive with the backgate because we push the lithium ion toward the device. And when you have a lot of lithium, a strange thing can happen. I'm sure that I'm sure that we will be able not to have intercalation at the gate voltage we needed. But in the process of doing these kind of devices and trying, we also see unexpected things that by now we are able to deal with. So I expect it will be possible, but for technical reason, we have not yet done it. So it's just, the technicality of having a device in which you're pushing quite a bit of lithium close to the device, and that can give a problem with chemical reactions, essentially.
Maybe I can ask a related question to this, because I was wondering something similar. So this is not the case for the conventional ionic liquids, because the molecules there, the ions are much bigger, so there's no chance that they will intercalate as they move.
Okay, intercalation with for the molecule, yes, indeed. The more, and also chemically they are much more inert. So they are at least with TMDs, you know exactly, I mean, we know exactly when you start to have a problem because you can look at leakage currents and if you start to have reactions with the liquid, which at some voltage will unavoidably happen because, you know, if you put enough energy difference, but we can exactly see them by looking at leakage current. So we can be sure we operate the device under condition when nothing bad happens. With lithium, we have less experience because we started much more recently to work, and lithium is more reactive. So there are things that we have to figure out how to deal with that we have not entirely figured out how to deal with when we go to positive polarity of the gate voltage.
Okay, so I don't see any other questions in the chat, so maybe I can ask the very last one, which is beyond like the TMDs, like what other kind of classes of pseudo materials do you envision this type of approach to potentially work to kind of
so materials that have been used
in the
material where people have done stuff which goes along the kind of thing I've shown you include, for instance, multi-layer phosphorine. I think Yoshi Iwasa measured the gap of fairly thick multi-layer phosphorine layers. Nanotubes, people have done this measurement on carbon nanotubes, for instance. We have been working on things like indium selenide. In indium selenide, the problem is that most crystals they have quite a bit of denser states in the gap close to the valence band, so it's very difficult to see ambipolar. Nobody has ever seen Hall transport in indium selenide because of these defects in the gap. I would expect if you would have enough clean enough material that would work. I think it's mainly a matter of having most, say, 2D materials that we know, they could work if they are stable enough and if they allow. For instance, there are some of the magnetic semiconductor. Those will not work, not only because they are chemically fairly sensitive, but also because they have very, very narrow bands. So you will not see good ambipolar transport because charge localizes. And so even if you put them in the valence band, one can develop other techniques. One can try to measure capacitances instead of the threshold voltage, and that might still be possible to do things by because then you don't rely on charge transport, you rely on charge accumulation, and you might be able to see that. So far, we have not done that, and I mean these materials I was mentioning, most of the magnetics are too sensitive to have reproducible measurement to air. I mean sensitive to the environment. But I expect that, with more patience and there will be more and more materials that work. So far, we have focused a lot on TMDs because we want to establish the technique, and it works fantastically well with those. So,
okay, so maybe very, very last minute question. I see one more popped up in the chat from Yuval Ronan. Yuval is wondering if it's possible to make a normal superconductor junction or a Josephson junction using ionic liquids, maybe by pre-patterning with metals.
I think I expect that yes, it will be possible. I think if in fact now that we are developing technique to do double gating, it might even be possible to to do a junction by accumulating charge on the opposite side of a flake, for instance. I think in one of the things that I have not mentioned, but it will be super interesting in the domain of superconductivity, of gate-induced superconductivity, is to see Hall-induced superconductivity by gating, because there is no reasons why you should not see it. Niobium selenide is essentially has the same band structure as molybdenum disulfide, but has the Fermi level deep in the valence band, and it's superconducting. But so far nobody has been able to get Hall-induced superconductivity, and that is one of the things we think that we know what are the conditions to do it. What I said is that when you accumulate multiple valleys, you enhance electron-phonon interaction. So we need to accumulate multiple valleys, but because of the energetics of these materials, you need a lot of charge density. So we have not yet been able to accumulate the charge density which is needed to see Hall superconductivity. That's something we're also working on.
Okay, so I think that's all for today. Thanks again, Alberto, for the very interesting talk. And
thanks to you.
Thanks, Naomi and Bob, for hosting us here, and thanks to everyone in the audience for attending. And I guess we will gather again in a week from now, or maybe not.
Thank you very much.
Thanks to you. Thank you, Ricardo. Thank you all.